Okay, I had to unmute myself first. So good afternoon, everybody. Thanks for participating. This afternoon, it's a presentation about sulfate optimization. And sulfate optimization is a topic that's dear to every cement producer's heart, but it's also something that that comes up and is very important when you develop new additives or when you work on new SCMs or existing SCMs and try to understand the kinetics of how things work, how different materials interact, because in effect it's one of the components that gets drawn upon by other other materials that you use besides cement. And sulfate balance is traditionally something that cement suppliers, if you ask them, they have slightly different answers as to how they do it and why they do it and what the ultimate purpose is. But eventually it boils down, I think, to trade-off of what you want your cement quality to be. It's of course a trade-off as usual between economics and performance. It's also a trade-off of what do you want your cement to be in the marketplace. And to illustrate that, I will first get to an example of two different cements that that we have encountered not too long ago. These are both cements that come from the West Coast. So they are, our US participants know that on the West Coast you would use typically type 5 cement, which is a lower sulfate cement. And you see two curves here, two sets of curves. On the left-hand side, you would have what we call OPC-A, and on the right-hand side, OPC-B. In fact, I'm seeing that it's mislabeled on the bottom of the left-hand graph. It should, both of them should be the OPC-A. So left-hand side is one cement, right-hand side is another cement. And what we see here is typical thermal power curves that you would normally see for a cement when you measure it in the isothermal calorimeter. And I assume a lot of you have already seen such curves and know roughly how to interpret them. And while there's many things that you could say about those, we're going to focus today on in particular on what you see about the sulfate balance. In both instances, both on the cement A and the cement B, we tested 100% cement mix and then 100% cement mix with some accelerator. With an accelerator, it's the calcium nitrate at a normal dosage level. And the sets of curves you see, so on the left-hand side, for example, you see the green curve is the 100% OPC, and then the yellow curve would be the one with the accelerator, which, as you might expect, you see the hydration starting earlier and going a little bit higher in intensity because it's what accelerators do. And when you look a little closer, you see the traditional sulfate depletion peak here. So the sulfate depletion peak is this little bump, this little notch you see after the main peak of hydration. The main peak of hydration is this larger heap that you see on the curve, and this is where the A light and B light formation comes into place for the strength building. And after you reach the maximum of that main peak of hydration, you usually get this little bump, which is a sulfate depletion, which means the resurgence of the aluminate reaction when essentially all the sulfate ions are depleted, the ones that were there to tame the aluminate reaction in the beginning of the hydration. All those ions are now gone, they're no longer available, and therefore you see the aluminates reacting again. Now typically what you want in a well-balanced cement where you have the right amount of sulfate, you would want the sulfate depletion peak to be a few hours after the main peak. And in both the cement A and the cement B, this is what you see. You have a nice peak. Now, what gets interesting is when you add the accelerator. Now, when you add the accelerator, you still see on the blue cement, you see distinctively, you see this peak of the sulfate depletion. It's a little bit shorter. The time between the maximum of the main peak and the sulfate depletion is a little bit shortened, but it's still clearly there. Now, on the other hand, on cement A, you're not sure if it's there or if it's not there. It might be, might be not. You would have to look closer, but it's not that obvious. So this could be an indication that in this particular case, well, a calcium nitrate accelerator might not work too well with cement A. Now, to verify this for sure, we would have to have a look at the actual heat of hydration curves, so the actual heat energy that comes out of the reaction and by itself. And here again, you have green and yellow cement A, and red and blue are the cement B. Now, green and yellow, you can see that the addition of the accelerator is kind of counterproductive. For the first maybe 15 hours, the yellow curve seems ahead of the green one, everything seems to go fine, and then things sort of collapse. Then eventually you get a performance that is not as good as your original cement without the accelerator. Whereas for the cement B, you can clearly see that from the red curve to the blue curve, you get an improvement by addition of the accelerator on total heat of hydration. And so what does this mean? This does not mean necessarily that one cement is bad and the other one is good. What it means is that a cement with a certain sulfate balance might be meant for certain applications and not others. So if you're on the West Coast and you tend to use accelerators because you also use maybe slag or fly ash, well, you won't find much fly ash on the West Coast except the one that you import, but natural pozzolans, other sorts of substitutes. So you're there and you want to use proper cement. Maybe cement A is not the best choice for this type of application. Maybe you would rather buy the other one, the cement B. For a cement supplier, again, it's a matter of choice. It's not that one cement is bad, the other one is good. It is it belongs to the cement supplier to decide whether they want to serve a certain market or another. But it's important to be aware of what the cement does. Therefore, as a cement supplier or as someone that sells cement and other materials, you should always try to be aware of what the market needs in your normal zone of influence from your plant, and you should test the sulfate balance with the materials that your customers typically would use. So you would not necessarily balance the sulfate for your standalone cement. You would balance it for the cement plus the additives that most of your customers would use in this area of the geographic area where you sell the cement. Now, of course, you have to keep this within standards, and especially being type 5 cement in this case, you would have to be very cognizant of what the standards say on maximum sulfate allowed. But it still is a choice. It's a quality control choice. It is a choice of economics and quality of what you want your cement to be. Now, with that in mind, and knowing that different cement suppliers have different objectives when they balance the sulfate, there's two things that I really want to touch upon today. The first one is, how can you easily find the right sulfate balance, either for your standalone cement, or if you use a cement with SCMs or with additives? How can you do this by using calorimetry? We are a manufacturer of calorimeters, so of course we see for us it's obvious that you can use those apparatuses for sulfate optimization, and we think, and many others think, that it's much easier to use a calorimeter than doing it the traditional way. That's the first topic that we want to touch upon today, and I will show you an example of how it's done just using a calorimeter and a simple software. The second one is about using a calorimeter for quality control. And what we mean is daily quality control, or maybe every other day or several times a day. So showing that the calorimeter can be an effective tool for frequent quality control, precisely because it's so easy to use and doesn't require a lot of operator involvement. And while most of you, or many of you at least, are familiar with how to find optimum sulfate using a calorimeter, maybe the second part of today's presentation you will be less familiar with, because it's quite new the way we try to approach this. And so first of all, how do we find the optimum with an isothermal calorimeter? Well, if we look back at how people do it up until now, for the most part, it's based on strength development, on compressive strength development. They follow the ASTM standard, and or they don't follow precisely the ASTM standard, but in most cases it's about doing strength cubes. And the way you would do this, you would prepare a mortar mixture with your cement, and you will prepare several mortar mixtures with the same cement and incremental additions of sulfate in the form of gypsum or hemihydrate or any source that you would use in your normal plant operations. And you would do cubes, many of them, and you would wait for a certain curing age, which is the age at which you want to optimize the sulfate level, and you would break those cubes at that age. So what does it mean? It means, well, for one, it's quite labor intensive. It takes a long time to prepare all those samples, and it's messy. And because it's cube strengths, you have to do repeat samples, because you cannot rely on one single result. You usually do 3, at the minimum 2, but usually 3 for each curing agent for each mix. So very quickly you get 20-something different mixes that you have to, or cubes that you have to prepare. It's inconvenient because your operator actually has to be there when you break the cubes. Say that you want to start your sulfate optimization process on a Friday, well, you're doomed, because if you want to do it at 24, 48 hours, you would have to come back on the weekend to do your breaks. So it is a big source of inconvenience. It has a certain variability attached to it, just by virtue of what it is, by virtue of how lab testing goes, and especially in a cement plant setting where only very few cement plants have a curing chamber and a proper lab to actually do those tests. So you get a lot of results that are quite uncertain, and you worked a lot to get that. It's not very efficient. So we say, could you use calorimetry to do this? Well, the easiest way to approach this is to show that there's a correlation between heat of hydration in joules per gram of cement, and that there's this correlation between heat of hydration and compressive strength. And this is not something new at all. So this has been known for a while and pretty much proven by countless studies and people that have looked into this. And the way you do this, you look at the calorimetry curve, and the curve you see here is a schematic, of course, so you have an exaggeration of some of the features, but essentially in the very early part, towards the y-axis, you see the first big peak, so big and narrow peak, tall and narrow peak of the aluminate reaction, which is not strength contributing. And you also have embedded in this first tall peak, you have embedded any imperfection for temperature shock because you opened the calorimeter lid, because you mixed materials that were not at the perfect temperature. All these things are embedded in there. Then you get to the dormant phase as you go down, which is sort of where your reaction calms down. And all the way until you get to initial set, this is a part that has nothing to do with strength building. So if you want to do a proper correlation between heat of hydration and compressive strength, you would eliminate that part. All the part that's shaded in red, we don't count. Everything that comes later, that's in green, that's the actual heat of hydration that you take into account when you want to calibrate or correlate it to compressive strength. And that is relatively simple, and the calorimeter does it for you. So you do not have to do complicated Excel spreadsheets for that. We have a software that automatically will do these steps for you, for the most part, or with minimal intervention from an operator. And when you do this and follow those simple recommendations, then you get to something like this. That's actually from a study that was done a few years ago. So it's a 2-year study that was done by Aalborg Portland. Aalborg Portland is part of Cementier, an Italian company now. So they're originally a Danish company. They have a few plants in the Nordic states in Europe, and they conducted this study. So for 2 years they were doing in parallel cube testing and heat of hydration, and they found a correlation that looks like what you see on the graph, which is excellent. But they're not the only ones. So you will find this at Heidelberg Cement, at all large cement companies, at Polsim. I should name them all just in case someone is here today that's part of one of them. But all cement companies have done at some point some sort of study where they showed that. Now, is that universally true? You will always find a good correlation like this? Of course, if you push it and you start playing with extreme values of alkali contents and other things that are a little esoteric, you might get out of range of this correlation. But now, outside of cases that you can quote in books, or that you can engineer to disprove that there's a good correlation, I think in general you will find that for the cement that's manufactured today in a normal cement plant, you will find a good correlation, excellent correlation between heat of hydration and compressive strength. Once you know that you have this correlation, things get easy. Now all of a sudden life is bright and easy when it comes to sulfate optimization, because you now can use a calorimeter by doing a simple dosage ramp directly in your sample vials. So instead of doing 20-something cubes or more that you then have to let harden in forms and come back at a specific time to break those cubes for the compressive strength testing, you just start with your simple low dose SO3 cement that you know is slightly undersulfated, and you use this as sample number 1. You see the 4 sample vials there. The one on the left is just a plain cement. And the next vial, you have the same plain cement, and you add a little bit of sulfate, or you substitute part of the cement with a little bit of sulfate. The third one, you add a little more sulfate, and the fourth one, a little more sulfate, and so on. The recommendation is that you would have 4 samples as a minimum. You can do more. You can do 5, 6, 7. We often do 6 or 7. And as you do those, of course, depending on what the capacity is in your calorimeter, you could do more or less of those samples. As you do those, it takes minutes to prepare those samples in those sample vials. It's really a matter of having the powder weigh the correct amounts, putting the water and mixing them either manually with a plastic spoon, as is actually shown in the ASTM C1702. You follow the procedure that's in the ASTM C1702. You could also use a vortex mixer. And then you drop them in the calorimeter, you load them in there, and you press start and you walk away. It takes minutes to do this. You do not have to be back at a certain time like you did when you had to do compressive strength testing with breaking the cubes. You do not have to monitor anything, to do anything special. You don't have to do repeats. This process is so repeatable that if you do it in this simple way, there's virtually no reason that it wouldn't work. You put them in the calorimeter and you walk away. You can go on your weekend trip, and when you come back after you're done, either 24 hours, 48 hours, whenever you please to choose your curing time for the optimization of sulfate, you can just simply interpret this in our software, and I'll show you in a minute how this works. Now, if you compare them side by side, you compare calorimetry and with strength testing, you'll see immediately, and the labor intensity is gone. It takes only minutes to do a sample preparation for calorimeter. The inconvenience of someone having to be there at a specific time is gone. The variability is pretty much gone for the most part. You don't require a curing chamber. The calorimeter is the curing chamber, and there you have a specific temperature that you dial into. And all this is done in a relatively limited space. You don't even need a very trained operator. Pretty much anybody can learn very quickly how to prepare those samples and press a start button on the software. So you don't need a specially trained lab operator to do that at all. And of course, those calorimeters, they do cost money. Like a curing chamber would cost money as well. But luckily, we have a choice. I do want to introduce this here and say there's no excuse today not to get one of those in a cement plant, because you can go from top to bottom. Top one is the model that we have that's most expensive. It's very precise. It's the highest precision calorimeter for this industry that you could find. You have flexibility. You could have a thermostat with 1, 2, 3, 4, or up to 8 channels. You could virtually buy the thermostat with just 1 channel and start with that, and then add them as you get the budget for it. You can add more channels to it along the line. It uses 20 milliliter vials. And then the 3 models on the bottom, they have larger sample vials where you can also easily do mortar, even some concrete testing, and they come in 2, 4, 8 channels. And here again, it spans a large array of budget availability, so there's no excuse. There's always a way to get this. Now, if you look at those models here, so depending on the number of test channels that you have, you can do other things that are not just sulfate optimization. You could very well, of course, do your ASTM C1702, and those they all comply with the norm. So the heat of hydration testing as per ASTM. You could do some benchmark testing with other cements that you have. You could actually look for changes that you see when you change something in your plant operation, like switch to different type of fuel, or you have a variation in the raw materials. All this can be tested, and as I said, it's relatively easy and doesn't require a trained operator for that. Now, once you have one of those and you run a test, as we just showed, you can just go into it's a very easy to use software interface that you see here. And you load those curves, and then you go from left to right. The first orange arrow indicates that you would you would cut out the initial part of the curve. As we showed earlier, you cut out the illuminate reaction and any disturbance that you would have before the dormant phase. And as you cut that out, you only keep with the strength building part of the hydration. So that's it takes seconds to do that. And the next parameter that you need to feed into our software is the actual content of SO3 that you had in your parent binder. That means in the cement before you added anything on top of it. The software cannot know it. Of course, you have to give the software this information, but you as a cement producer would typically know this because you're the one that manufactured that cement, and at some point you tested it, you measured it. So you feed this information. In this case, this cement had 3.25% of SO3 in the binder before we optimized. And then you have to tell how much sulfate you actually have in your sulfate carrier that you used. So if you use a gypsum, it depends on the purity of the gypsum. If you use a hemihydrate or something else, or a mix of those, or whatever source you have of SO3, you would have to tell the software in the powder that I add how much of that powder is SO3 in percent. And in this case, it was roughly 47% was SO3. When you feed in this information, then the software immediately gives you what the optimum should be. So software calculates it, fits it to this inverted parabola, and in this case, the optimum turned out to be 3.6%. So the original cement had 3.25, and this optimum here shows 3.6%. Now, of course, we did an optimization that was really only based on compressive strength development. Now, we're not naive. We know, and we know from our customers, we know because we're from the industry, that there's other criteria that comes into play, that you don't balance sulfate just on strength alone. Rheology is a chief criteria that you hear very often, where people say, I'm in my plant, I balance my sulfate, sure, I do the compressive strength testing, but I have to adjust. I have to adjust because I need to reach a certain rheology. And if I don't reach that, then my customers are unhappy. But the problem with rheology testing, of course, it's not just slump. It's a little bit more complicated than just testing slump. And the rheometers that are out there now in the market are not necessarily very good for concrete testing. Actually, they're not good at all. What you find is either for paste testing or at the very best, if you're lucky, you can test some water in there, but not concrete, or you find some that are good for field QC testing, portable rheometers that work somewhat for concrete, but they're not robust, they're not reproducible. It's not equipment that you would have in a QC testing lab. So we also offer rheometer, not only calorimeters. We have a rheometer that is designed for concrete testing. It has a specially shaped impeller, it has a planetary motion, it keeps the concrete mixed while it measures without segregation. Because if you use a conventional rheometer that was not designed for this, and you put it with a very heterogeneous material like concrete, where you have these large particles, you do get segregation. What you end up measuring is not rheology of concrete, you measure rheology of one of the phases, and the aggregates sit on the side or on the bottom. So it doesn't give you anything that's really meaningful. Now I can actually play a little video here, I think. I thought where I can show how this thing works. Hold on. So I hope the video shows okay. But you see there's a planetary motion to keep the things mixed, and you'll see in a minute when the actual concrete is in there. The vessel is relatively large, so you can have large particles in there. And this is how it looks. And you could virtually measure the rheology in there from inception of the concrete, when the materials first go in there, all the way until initial set. So you can measure for a very long time, get the complete picture, and this works from zero slump concrete all the way to a liquid. So the whole range of possibilities is covered, and you can even test fibers in there, by the way. So if you do think about testing not only compressive strengths or calorimetry for sulfate optimization, you think about rheology, well, this may also be something that is worth looking into. Now, with that being said, I want to talk about something else you can do with your calorimeter. You can optimize your sulfate on the spot, And you can do this regularly, maybe every month, every week, whenever you feel like it, because it's easy enough. But there's something else that we ought to do here, because if you think about quality control of cement, you got to think what the important criteria is in quality control. And I can draw from personal experience a little bit here, because I worked for Lafarge a few years back, quite a few years back indeed, and that was in Atlanta. And I worked, which is now actually the Argos operation. And I worked on the cement side, and we would go around customers. We were very proud of the quality of our cement, of the performance versus other things you found in the market. And so we go and ask customers what they thought about the performance of our cement. And one customer from Alabama put in pretty crude words, and he said, look, Mark, I really don't care about the performance of your cement. You can sell me crap as long as it's consistent crap. And if you think about it, it makes a lot of sense, because a concrete producer in a given plant has a few hundred mixes. And concrete trucks go in and out, and there's new mixes pretty much every day that you have to draw upon. And you know, what you least want to do is have to redesign those mixes every time you'd have a new job. So what do concrete producers do? They over-design, because they know that not everything is consistent, and they know that there's differences and that there's imperfections, so they over-design. It costs them money, it costs them time, it costs them grief, and of course they don't want customers to come back and say your stuff does not work. So if you want to do a concrete producer a favor, deliver consistent product so that he knows what to expect. He doesn't have to adjust day in, day out. Everything is nice and happy. So what's a good criteria to deliver this consistency? So we looked at our calorimetry curve, and we said, there's more you can take out of that. There's something that's an important parameter when you look at it. And we thought about it as the distance in time, so the period in time that goes from the maximum of the main peak of hydration to the onset of the sulfate depletion peak. So not the maximum of the sulfate depletion peak, that's where it starts, right? This is indicative of whether there was enough sulfate in there to get the strength reaction, the strength build in the A light and B light, to get it all the way through so the strength builds nicely. And this is a good criteria to look at for the consistency, because any deviation will be very quickly seen in the difference between those two peaks. Right? So for example, if a cement plant goes and uses a new type of fuel, you will see a difference in there. If you have variations in your raw material, you will see a difference in there. Right? And so what you do in this case, if you look at this difference in time, you can use this as your quality control parameter. So if you could find for your cement, for your market, with the SO3 level that you choose, if you could find the optimum time or the time that corresponds to the optimum SO3 level between the maximum of the main peak and the onset of the sulfate depletion, and you say, well, as long as I'm around this exact time, every time I crank out my cement and it comes out of the mill, I'm good. So what you want to do, you want to probably take a grab sample every so often and then see how you stand on this quality control parameter, and we call it delta T SO3, as you see there on the bottom of the graph. So you want to monitor your delta T SO3, and the way to do this, so if you remember from our example that we had before, we had a cement that was originally 3.25%. We actually saw that 3.6% SO3 was the optimum for this cement, and the 3.6%, so the peak of that parabola, this inverted parabola, is between the yellow and the red point. The yellow point was 3.5% of SO3 in our dosage ramp, and the red one was 3.75. So somewhere in between those, you have 3.6. So what we can do to find out what the delta TSO3 would be for our optimum, we just take the delta TSO3 for the yellow and the red. So if you look at the right-hand side graph, we did that. For the yellow curve, you have a time between the maximum of the main peak and the onset of the sulfate depletion peak of 90 minutes. And for the red curve, it's 165. Then we just plot that. We make a plot where we say, let's just draw a line, make a linear interpolation of those 2 points where we say, well, on the x-axis, we have the percent of SO3 in the cement, On the y-axis, we have those delta T SO3 for those 2 points, and then we position ourselves in between at 3.6% where our sulfate optimum is. So we go to that point, and we say that we see that on the y-axis we get to 120 minutes as the ideal delta T SO3 for our optimum sulfate. So we say when we're at optimum sulfate, the sulfate level that we want for our cement, then we actually have a delta T SO3 of 120 minutes. So that now becomes our target. We want our cement, when we produce it, to always have the same 120 minutes between the main peak and the onset of the sulfate depletion peak. So with that in mind, we can have a very simple quality control procedure. And that is, when we take a grab sample from the mill, which for many companies can be several times a day or at least once a day, we might as well take one of those samples and make a quick calorimetry sample out of it. It's so easy to do. It takes a few minutes. You take that sample, you put it in a little sample vial, you add preconditioned water to it, drop it in the calorimeter, and you're done. So in a few minutes, you put this in there, and sometimes after 10, 12 hours, as soon as you reach the sulfate depletion peak, you will have an answer as to where you stand on your current quality of cement. And when you have a variation, you can correct for it. Now, the good thing about all this is that all those things like looking up those times between the main peak and the onset of the sulfate depletion peak, drawing that linear interpolation, finding what it would be for the maximum sulfate, you don't have to do it. Our software does that. The only thing you have to do is to run the test, to prepare the sample. Here goes 3 minutes of work, and then load the curve later on in the computer, which takes another 2 minutes of work. And the software does everything else. The software calculates what those times are between main peak and onset of sulfate depletion peak. It compares this to what your ideal target parameter is, and it will also suggest a correction factor where it says, well, if you want to go back to your 120 minutes, if you're off, you can just add a little bit of sulfate, or you can take a little bit of sulfate out, use less. And the way it does that is very simple. So this is in this example, this is another run from a mill grab sample where we exercise the quality control parameter. So this cement, as we saw, had 120 minutes ideal quality control parameter. That was our target. So on a different day, when you take a grab sample out of the mill, you would get to a value here of 95 minutes. So you see, in this case, we ran it for the test. We ran it for 12 hours. You could have stopped this at 10 and get this result. So here you get 95 minutes where we actually want 120. And what the software does in the background, quite conveniently, it takes the linear interpolation we had from before. That was the simple linear equation of y equals 240x minus some constant. You take this and you can calculate from very easily, of course, from the difference between those two times, the 120 minutes and the 95, you can calculate what difference of SO3 percentage you would need to get back on track. And in this case, adding roughly 0.09, so let's say 0.1% of sulfate to the optimum you had before would get you back on track. So why is this important or convenient? It is because by using a calorimeter in any cement plant without having a lab, you can virtually have this in a room. These things are designed to be working very nicely, even though you're not in a very well air-conditioned space, even though you're not in a lab space. You could take anytime a grab sample from the mill. In minutes, you could prepare this and get it in the calorimeter, and you would have something where you can do almost daily quality control to ensure consistency of your cement. And of course, to see at any time if something looks odd or out of the normal, then you can trace it. You can trace it back to what the root cause is. But it's a very easy, convenient way. And besides telling you something about optimal sulfate and whether you have a certain consistency in your manufacturing, well, it's a way there to have a continuous curve of how things happen. You continuously see how the kinetics of your reaction unfolds. So you have something that you can use to trace it back to certain problems. If something does not look right, you can analyze it and you can see what's happening on the rest of the curve. So it's a very, very powerful tool. Now, of course, those who have used calorimetry will say, well, in the real world, it's not exactly that easy because I actually have to precondition the water. If I use a certain water amount for the preparation of my sample and this water is not at the exact same temperature as the calorimeter, I'll get junk results in the beginning of the curve, which is true. So this conditioning the water means, oh, I have to put water at least 2 hours into the calorimeter before I start, then I have to come back, prepare the sample, it takes logistics, and then of course if you don't have the same operator every day in the cement plant, there's also a point to be made that you could have some variability because different operators mix differently, they have different procedures, so it's not completely perfect. So in order to get rid of all those unknowns and all those nuisances, we said we might as well develop something that is automated, right? So take away all the worries, and we developed an automated mixer. Some of you might be familiar with other types of mixers that you use and that come from the outside. You have a little stirring mechanism that comes from the outside, but these are no good. And we don't do those and we don't sell those because they're no good. And there's many reasons we can get into these, why they're not good. But what you really need is something that you place inside of the calorimeter with your sample in there, where you have your cement powder and you have the water, and they're not mixed yet. They're in separate compartments. And it sits in the calorimeter for an hour, so that, or maybe 2 hours, and so that the temperature of the materials gets nice and stable. No one opens it, no one gets even near, and then after 2 hours, the water gets injected into the powder, to the cement or the binder, whatever it is, and it starts mixing. And on top of this, this mixer has a relatively high torque motor, so you get a realistic mixing energy. It mixes well, and there's lots of parameters that you can change to ensure that it mixes well. So you can look at mixing speed, the angular steps. You can do rotations that are, for example, 270 degrees clockwise and then 45 degrees counterclockwise, and go in steps like this. All these are parameters that you can change and you can touch. And you have now an automated system where you just put your sample in, you walk away, you don't have to wait for 2 hours then come back and mix something. This is all done in there. It's not only easier, but it takes away all the variability that you could suspect there was before. Right? And I also have a short video that shows how easy it is to assemble those when you prepare your sample. Here again, I have to, I have to get back to, it's done, here you go. So you have those different parts. This is the cement in the vial, and you put the impeller in. So you, with a rotation movement, because it's otherwise it will not penetrate into the cement powder. Then you assemble the motor on top. It takes not long, like a minute to do all this. And then once you have your cement on the bottom, you have a water compartment on the top where you can add the water quite easily. In this case, it was 50 grams of cement and 25 milliliters of water. So all very standard. And when you're done with that, then you can just take that mixer and insert it into one of the calorimeter cells. And then well, you have to plug in a cable, of course. Now everything nowadays is Wi-Fi, and it seems very low-tech if we use a cable, but on the other hand, everything that's Wi-Fi needs a lengthy setup system, and it's not compatible with everything, so cables are still the way to go if you want it to be reliable. It's a flat cable, it's very robust and everything, so no problem with fitting between the lid and the actual temperature chamber. And then you're done, so it doesn't take long, and this is what it would look like if you saw how it mixes. So you can see by transparency on the bottom a little bit, you know, the water just comes in now and gets mixed in, and then there's first a rotational movement to just mix the water in, and then there's a different movement. There has some oscillations built in that goes back and forth to mix properly, and the torque applied here was a half Newton meter, which is, well, for this size sample is quite large. So you see, in conclusion, and now of course boasting a little bit about the nice products we have, we have everything that would be needed and useful for sulfate optimization in a cement plant or for a setting where you do research about this or other things. As I said, we have calorimeters for pretty much every budget. We have software that I believe is relatively easy to use because a lot of it is just push button. It knows what you want. It says this is a software for sulfate optimization. Well, load your curves, input 2 parameters, press a button, here you go. We have the automated mixer to make your life easier. And we have the Rheometer for those who want to go a little bit beyond and please their customers even more by having studied the rheology of the different products that they sell. So with that pretty much concludes what I had to say today. So I want to open it up for questions, of course.
Thanks a lot, Mark. That was great. So folks, we've got time for some questions. If you have a question, you can use the chat box. We do have a question here, Mark. Do you run SO3 optimization with different phases of gypsum?
Okay, so I'm not entirely sure. I understand the question is.
Paul, let me actually. Paul has. Paul, I've unmuted you. If you unmute yourself there, if you would like to talk about that, you certainly can. But basically, Paul's saying.
Okay, I'm online now, so yes, you can certainly do that. For example, you can look at hemihydrate versus natural anhydrate and those things, and many people do that. In fact, it would be the same procedure as I showed now. It would just be that you use different types of sulfate carriers. And having said that, you can of course also decide to include SEMs in the test if you want to, or a chemical admixture, because this type of testing is not at all sensitive to bleeding like a normal compressive strength testing would be.
Okay, great, Paul. Thanks, Brian. Hopefully that answered your question. If not, you can add additional thoughts there. Mark, I will one other question that came up this morning, and I'll go ahead and ask it here, and that is the impellers on the mixer and whether they're reusable.
Well, that depends on how long you leave them in there. Of course, especially in the initial stages when we tested the first impellers, we had different shapes, and we didn't want to manufacture too many of those without knowing what they do. We would reuse them, yes, by ensuring that we take the sample out before it sets and then cleaning them thoroughly. But generally, when you leave them in there beyond set, if it's beyond just testing if they work properly for mixing, they're disposable. You cannot really take the cement out. There's no way. So that would be a consumable.
Okay. Thanks a lot. So a couple other questions here. One question is the time of 120 minutes between the main peak and the sulfate depletion peak. What's the fundamental basis for this? Or is this only a suggested value that works for a specific cement?
Oh yes, this is not a universal value. This is for this particular cement, it happened to be this. So what you would do for your cement, any cement that you have, you take your cement, and they will all be different, and you look at what your optimum sulfate would be, and then one way or another you infer for your optimum sulfate how many minutes you would have between the maximum of the main peak and the onset of your sulfate depletion. And for every cement, this will be different. And in fact, it will also be different if you want to optimize your sulfate at 24 hours of curing age or 48 hours, 72 hours. That's for you to choose as a cement manufacturer or someone who wants to optimize this. So you choose your optimization age, you take your cement, you do your optimization, and you will get the number that's right for you. And this will be your quality control. And this number is, for one, it's not universal, and of course it changes depending on what you want to do with your cement. If you want to target a different market, if you want to have a different sulfate optimization, if you use a different sulfate carrier all of a sudden, you have to redo the exercise.
Okay, great. Thanks, thanks, Mark. Nick, hopefully that answers your question. If not, certainly you can ask an additional follow-up. the other question that came up here is Jeremy is asking, how much does an 8-channel model typically cost? Jeremy, the systems range on the low end from around 22,000 to an 8-channel is typically up in the low 40s for the HPC models. So that's the range that we're talking about. The mixers themselves are additional options that can be added per channel, and those are about $1,800 per mixer, with discounts available for purchasing 4 or more. So that's the range that we're talking about. The other thing I'll mention on that is, if you're not aware of this, on the HPC models and the Ultra model, those are all available as through our rental program, which is very convenient in a lot of situations, either because it's easier to get expense money versus capital, or if you just want to, build support within the organization to prove the value, which we're confident if you rent a unit that you will that would be the case. So anyway, hopefully, Jeremy, that answers your question. All right, other questions that anyone has? We're going to stay online here for as long as anyone is still connected in, and so we certainly are available. Paul Sandberg is still online as well. Paul is also with Calmetrix and is a recognized expert in cement chemistry, so you could take advantage of that as well. As you leave the presentation, we certainly appreciate your participation, and of course you can always contact us offline as well with the contact information that Mark had on that last screen. Thanks for attending, Nick. Appreciate it. Thanks, Jeremy. Have a great day. You're welcome, Hader. Thanks for joining. There is one question here, guys, from David. And are the curves valid for fly ash blends with cement?
Sure, the curves are valid. You could do any test in the calorimeter with any binder that you want to use, and you can do sulfate optimizations for cement with fly ash, and you actually should. Cement suppliers don't typically do it for all the possible combinations of what's used in the market, but if you're a user of cement and fly ash, you should be aware of what the optimal sulfate would be. Some fly ashes don't change a thing and are inert to that, but typically class C ash or anything that has a little high calcium, slags as well, would have a very strong impact on sulfate balance in particular, and other things.
Okay, great. David, hopefully that answers your question, but again, if yep, okay, great. Thanks, David. All right, just a couple folks here. I think we're just about here at the end, guys. So for the others, a couple others that are still online here, I'll give you another minute if you would like to to ask a question. Jeremy, on your question about a copy of the presentation, yes, what we will do is we'll provide a recorded version of this for everyone that registered, so that will be made available within the next couple days. So hopefully that will satisfy your need there. Okay, well I think that concludes our presentation for today. I greatly appreciate your attending if you're still online. If not, and certainly you can get in touch with us if you have additional questions. Have a great day and thanks a lot.
Thanks.